you, I will literally murder
So
you.
you're not going to the game.
Wow.
I hope we don't lose.
We
already lost the
My
list.
Lord and Savior Kiel.
Leave your bag?
Yeah.
Yeah, but it was like JV. But still, that's like embarrassing. Yeah.
Right, that force is just the sum.
Second class students, if you have to, we will make it, if you have to.
We all have issues. Probably at volleyball again, is my guess.
I knew you were going to say that.
Teachers, faculty, staff, please close your doors and send any tardy students to secure meeting room. Thank you.
All right, make sure your name's on the homework. Those chapter 4 questions from the text, please. Pass it to the right side. There we go. Thank you. Okay, so the chapter 4 questions from the text. Thank you.
You guys have
You
it.
guys got those there? Pass it over. Thank you.
I'm sorry, it's,
Just don't make a mess.
I promise I won't, I'm very tight.
Why do you?
All right, please take out your notes. Please put away. Hardy, pass. It's not a habit of yours. All right, everyone, listen up, please. Okay, so last time in class you got a qualitative introduction to Newton's laws. Today we start to work through quantitative examples. As I do this, it's going to look like almost exclusively that I'm using F equals ma, Newton's second law, to examine situations. But Newton's second law, F equals ma, is the mathematical heart of motion. All three of the laws of motion, however, work together simultaneously in situations to describe whatever it is that occurs. However, mathematically, the heart of dynamics is in fact Newton's second law. This is always where we start mathematically when examining situations. Now, Newton's second law is the following rather deceptively simple-looking equation, F equals ma. Remember what the various symbols here mean from last time. For example, here on the left-hand side of the equation, this here refers to the vector sum of the individual forces that are acting upon an object. So all of the pushes and pulls that act upon an object in some manner. This is the vector sum of the individual forces. And then the right-hand side of the expression is the net result of it. Whatever those forces add up to, they add up to some number in some direction. The number itself is referred to as the net force. But then how much acceleration occurs doesn't just depend upon how the forces add up. It doesn't just depend upon the net force, it also depends upon the mass of the object itself. Remember that mass, sometimes called inertial mass, is a measurement of inertia. The greater the mass of an object, the greater its tendency to remain at constant velocity. So mathematically today, we'll begin working with this expression. I'm actually going to start with the following example. I have this set up as a very simple demonstration here on the side counter. Right now, acting upon this object, there are actually three forces. The strings are pulling on the object. Forces associated with strings are referred to as tension. And then, of course, we have the force of gravity acting upon the object's weight. All three of these forces here have to add up to zero. And they have to add up to zero in every possible direction, because the acceleration of the object is equal to zero. It's just sitting here at rest with respect to us in the classroom. It's in equilibrium, as we say. And so then therefore, all the forces here vectorially have to add up to 0, and they have to do so in every possible direction. If they didn't add up to 0 in some specific direction, then the object would accelerate in that direction. It's obviously not, it's just sitting here at rest, so therefore all the forces add up to 0. So let's go ahead and give that example there, that demonstration, some numbers. And I tried to match up my demonstration here with the numbers that are given here in the problem. Okay, now the mass of the object itself is 200 grams. We do, by the way, for the most part, work in metric SI units at the introductory level, so I will have to think of that as 0.2 kilograms when I numerically run through the example in a few minutes. Remember that there are 1,000 grams in 1 kilogram. Okay, the angles made by the strings with respect to the horizontal direction are 30 and 45 degrees. I tried to set that up with the demonstration. So as I face the counter on the right-hand side, that's the lesser angle of 30 degrees. On the left-hand side, that's the greater angle of 45 degrees. So what I want to calculate is what's called the tension in each string. This is the force exerted on the object by the two strings. Okay, once we run through the example numerically and then calculate out the tensions, I actually have spring scales over there on the side attached to the strings themselves. We'll see exactly what the spring scales read. Note, by the way, what it says at the bottom of the screen. I've been kind of waiting for that all semester. I've been waiting for that bulb to wear out. It's been a while. Okay, now we begin a problem in dynamics that is using F equals ma in the following way. We first of all note the mass of the object in metric SI units is 0.2 kilograms. And then we start by drawing what's called a force or a free body diagram. It's a vector representation of the forces acting upon the object. So in this case, with the object over there in the side counter, we have the following three forces. First of all, we have the object's weight. That's the force of gravity, mg straight downwards. And then secondly and thirdly, we have the two strings. So as I said, the way that I have it set up is on my right as I face the counter, like so. This string here, we'll call its tension T1. With respect to the horizontal direction, makes an angle here called theta equal to 30 degrees. Okay, then I have the string on the left-hand side. That kind of looks something like this. We'll call its tension T2. This one here is at a 45-degree angle. So with respect to the positive x-axis, or the positive axis, excuse me, the horizontal axis. This right here, we'll call it angle phi. This right here is 45 degrees. Okay, now here's how we go about approaching F equals ma. First of all, we note immediately that the right-hand side of the equation is equal to 0. The object is just sitting here in equilibrium. Its acceleration is equal to 0. And then, as I said earlier, the forces here have to add up in every possible direction to 0 because the object is at rest. It has an acceleration of 0. The easiest way to go about doing that mathematically is just to break everything up into components in the horizontal and vertical direction. So in the horizontal direction, as always, we'll think of that as the x direction, and in the vertical direction, we'll think of that as y. So I begin to approach the equation F equals ma, first of all, by taking a look and seeing what happens vertically, or horizontally, excuse me. I'm going to sum up the forces in the x direction first and set that equal to 0. What I have to do is I have to take the force vectors T1 and T2 and break them into components. I actually have already kind of started to do that by noting these angles here, theta and phi, in the example. Notice T1, first of all, for example. It has a component here in the x direction, like so. That's going to be T1 cosine theta in just a moment. And then right here, it has a component in the y direction. That'll be T1 sine theta in just a moment as well. And then tension T2 here has its own components. It has this component here horizontally. This is a T2 cosine phi, and it has one here vertically. This is a T2 sine phi. And now here's how I add everything up. Basically, in the x direction, This component here and this component here just cancel each other out. The easiest way to write this, however, using the equation F equals MA, is simply to do the following. Think of this one here to the right-hand side as positive, and think of this one here to the left-hand side as negative. So I'm going to add them together then in the following manner. Right here is T1 cosine theta, and then I'll add to that a negative T2 cosine phi for the opposite direction, and then set it equal to 0. Okay, that equation I just wrote down in red is F equals MA. It's the sum of the forces here horizontally equals the net force horizontally, which is equal to 0 because the object, once again, is at rest. Now, in that red expression, you notice that there are two unknowns, T1 and T2, so I need another equation in order to algebraically solve the problem. This is done by obviously summing up the forces in the y direction. So the sum of the forces in the y direction is also going to equal 0 here, because once again, the object is not accelerating, it's just simply sitting there at rest. So everything vertically now basically has to cancel out. So let's call up positive and down negative for doing this. Right here, for example, is going to be a positive T1 sine theta. Right here is a positive T2 sine phi, and they're going to be then canceled out by mg in the opposite direction. So I sum up the forces here vertically in the following way. T1 sine theta plus T2 sine phi, and then minus mg because it's in the opposite direction, is equal to 0. So that expression right there, once again, is F equals MA. This is the sum of the forces here vertically, adding up to the net force vertically, which is equal to 0 because the object is at rest. So algebraically now, at this point, it's rather straightforward. All that I end up with are two equations and two unknowns. So what I'll do is take this red expression here first. I'll solve it first for T1, and then once I have that, I'll plug it into the second expression here, where then my only unknown will be T2. So, doing the algebra at this point, let's move this term to the right-hand side first, like so. And now I'll divide by cosine theta on both sides to get T1 here by itself. And now I take that expression there for T1, and I then plug it into the other expression. So doing so, over here on the left-hand side, I have T1 sine theta, so that quantity there, like so, times the sine of theta. And then I have the middle term there, plus T2 sine phi. Let me go ahead, by the way, and move the mg here to the other side. And I'm going to just solve for T2 here. I'm going to do two minor steps here at once. I'm going to first of all factor out a T2 from each term here. We'll also note, secondly, that sine over cosine of theta is tangent theta. So doing a couple of minor steps here at once will then therefore give us this. And now I just divide by the parentheses on both sides to get T2 by itself, which will then give us this. Now when I plug in my numbers here to solve for this force, whether it be T1 or T2, I'm ultimately going to end up something that's in terms of newtons. The reason for that is the following. Here in the numerator of the expression, we have weight, which is in newtons, kilograms times meters per second squared, and then a denominator, we just have a bunch of trig terms, which remember have no units whatsoever. So the basic metric SI units of force, in this case tension T2, is in fact in terms of newtons. And now we just do that. So in the numerator of the expression, 0.2 times 9.8, and then divided by all these trig terms. So that gives us cosine of the bigger angle, 45, times tangent of the lesser angle, 30, plus then sine of 45. And this comes out to be about 1.76 newtons. We usually abbreviate newtons as capital N because it's somebody's name. Okay, now that I have that expression for T2, that number that is, we just jump back up here to solve the problem, remainder of it, and get our answer here for T1. So just plugging in, I still have T2 here in my calculator, and then times cosine of 45 divided by cosine of 30, and this then yields about 1.43 newtons like so for its magnitude. Okay, now let's see how well we did here with our comparison. As I said a few moments ago, I have some spring scales here attached to these strings. Let's see exactly what they read. So first of all, here's the lesser angle of 30 degrees. This right here, remember, is the tension T1, which is found a moment ago to be a little bit less than 1.5 newtons. So take a look, Zach, you're rather close. Right here is 1 newton and there's 2 newtons. Are we about halfway in between the two?
Pretty close.
Yeah, pretty close, like so. So that's about 1.5 newtons. And then the T2 was 1.76 newtons, about 1 3/4. So that's this guy right here at the 45-degree angle. So Zach, is it closer to the 2 as it is to the 1? Yes, it is. This right here is pretty close. Now, one thing about my demonstration here, however, to notice is that notice that the spring scales are not attached directly to the object itself. Yet it is still giving us correctly the tension associated with these strings. Why is that? Well, there's a few things to mention here about strings. You're going to encounter strings in basic problems very commonly. The reason for that is because they connect objects together, and the force associated with strings is rather easy and straightforward to deal with. Okay, we do, however, start by making an idealization. We compare the mass of the strings to the mass of objects in the problems, and the mass of the strings is pretty small in comparison. So we basically ignore it. We consider the mass to be negligible, so they're massless strings. They have no weight. So what then happens when you pull a string taut, as is occurring, for example, in this example? Well, when you pull a string taut like so, in reality, does it sag a little bit under its own weight? Yeah, it does in reality, but we're ignoring that complication. So when it's taut, it's a perfectly straight line. It's horizontal in this case, or on these angles, for example, in this problem. So when the string is taut, that means it's a perfectly straight line. That's because we're ignoring its negligible mass. But when a string is taut, it also means the following. Okay, let's say that here's a taut string, and then we just take a look at individual pieces of the string. So individual segments like so. Okay, each individual segment is under the exact same amount of force. You'll see why in just a moment. Well, let's say that, for example, this segment right here, when it's pulled taut, is being pulled in this direction and in this direction. And then say similarly over here, this guy over here is being pulled in this direction, in this direction. The value of those blue force vectors there, the tension itself is the same at all points along the string. The reason for that very simply is the following. Imagine taking a look at this little segment of string right here, and let's say that it was being pulled to the left-hand side here with more force than to the right-hand side. So then therefore, what would this segment of string start doing here relative to these guys? It would start accelerating in that direction. That's obviously not happening. All the segments of the string are remaining the same distance from one another. This then means that the tension is the same at all points along the string. So when you encounter strings in problems, they're always straight lines, we ignore their mass, and the value of the tension is the same at all points. Okay? Okay, next. I started my numerical examples here with a situation involving an object at rest, where the acceleration was 0, and then all the forces cancel out as we went through. However, in the next example, let's say that the forces do in fact cause an acceleration. How do you then approach the equation F equals ma? Okay, with this next example, we'll also use it as kind of like a bridge in going between what we did in chapters 2 and 3 with kinematics to now here in chapter 4 with dynamics. Zach, your question first?
So when you're looking at F equals ma, you say ma is net force. That means the total sum of the forces.
So it's the total numerical sum of the forces added up as vectors. In this last example, of course, it was 0. In this next example, it's not going to be. We're going to go about calculating.
But I mean, and then F is the total
So just
vector
the
sum.
F in the F equals ma, the left-hand side of the
Yeah.
equation is adding up the forces. So up on the top board, for example, the red equation there, the left-hand side is the F, the sum of the forces horizontally.
Okay.
You'll see it happen here in this problem as well. So as I said, this is a nice problem to go from, say, what we did back in chapters 2 and 3 to now here in dynamics. Notice that some kinematics quantities are being described in this example first. What we'll do is just a little bit of basic chapter 2 kinematics and find the acceleration. But back in chapter 2, that's all that we would have done. Now we'll go one step further and we'll understand exactly how the forces acting on the hockey puck in this case cause this acceleration. And I'll demonstrate this using my eraser in just a few minutes. Okay, now if we saw this back in chapter 2 with the kinematics that's being described here, then all that would have occurred is the following. Okay, we'll just start the object at the origin, x1 is equal to 0, and we're given an initial velocity here to the right-hand side with a magnitude of 5 meters per second. If the puck comes to rest over here, its final velocity is 0. It then therefore undergoes a displacement x here equal to 10 meters. Now in terms of the kinematics of the problem, this is a pretty simple example. All that we'll use here is the third kinematics equation to figure out what the acceleration is. So back in the good old days of chapter 2, here's the third kinematics equation. And then we just start by plugging in our zeros, eventually trying to find the acceleration. So the zeros are as follows. Final velocity is equal to 0, and the object starts at the origin. Like so. Okay, then move the v0 squared to the other side of the equation. You pick up a negative sign when you do. And then divide by 2 times x here to get the acceleration by itself. Like so. And then numerically we just have the following as if we would have done this back in chapter 2. So v0 squared is 25 divided by 2 times 10, so divided by 20, and this ends up being negative 1.25 meters per second squared. And we would have noted back in chapter 2 that as the object is moving to the right and slowing down, the acceleration vector being negative means that the acceleration vector points to the left-hand side. And that's basically it. That's all that we would have done back in chapter 2. And now we want to understand what causes this. So now we start to take a look at the dynamics of the situation. So now imagine that the hockey puck is my eraser here. And then the problem begins not while the eraser is in my hand, but the instant that I let go of it. The instant that I let go of it, the kinematics on the top forward happens, and it just merely looks like this. So while the eraser is sliding to the right-hand side, after I let go of it, how many forces are acting on it? Watch it once again after I let go of it. So, can anybody tell me? So vertically and horizontally, how many forces are acting on the eraser? 3. Now some of those forces are pretty obvious. First of all, we have the force of gravity downwards, and G. And does anybody remember from the very end of class last time, what force is acting on the eraser upwards, Jenna? Okay, we'll get to the horizontal situation in a moment, but Ryan?
Normal force?
Yeah, the normal force. The normal force is abbreviated as capital N. Now remember where the normal force comes from. It comes from Newton's third law. Gravity causes the eraser, for example, to press down on the desk, and then therefore the reaction is that the desk presses back up. That's the normal force. The reason why it's called normal is because in mathematical lingo, the word normal means perpendicular. So it's perpendicular to the surface. Okay, now Jenna, horizontally, what other force acts upon the eraser and in which direction? Okay, the force of friction. And if the eraser is sliding to the right, in which direction does friction point? To the left-hand side. Like so. Friction, by the way, is usually denoted as small f. Now notice that specifically it is the force of friction that gives us the acceleration to the left-hand side. Now from the kinematics on the top board, we already know that the acceleration is to the left-hand side. We calculated that. We're now getting an understanding as to what is causing it. In this case, it's the force of friction, obviously, that's slowing down the eraser. And now we begin to add things together using F equals ma. Okay, vertically, what can I say immediately about the normal force and the object's weight? Yeah, they cancel each other out. The reason for that is because there's no acceleration horizontally, or vertically, excuse me. Now, you could say this a couple of different ways using F equals ma. You could call up positive, for example, and down negative, and then therefore the sum of the forces would be written in the following way. N minus mg is equal to 0. So I have here the sum of the forces vertically equals the net force vertically, which is equal to 0, because there's no acceleration in the vertical direction. Or equivalently, you could just say directly that the normal force is equal to the object's weight. That's obviously what the above expression implies. Okay, then we take a look now and see what happens horizontally. Horizontally, we do have an acceleration to the left-hand side. Notice, by the way, that there is no force vector acting on the eraser or the hockey puck to the right-hand side. So is it possible in this situation for the hockey puck to speed up in this direction?
No.
No, because there's no force acting on it to the right-hand side. The only possibility is that the acceleration is to the left, thereby meaning that the hockey puck slows down. Now, here's how you add everything up using F equals ma in this horizontal case. What we do by default, just because it's easy to deal with, is we always think of the direction of the acceleration as the positive direction. And then therefore, any force vector that points in that direction is a positive number. Any force vector, if it was present pointing in the opposite direction, we would think of as negative. So then therefore, in this simple case, when I add up here F equals ma, we have nothing more than the force of friction is equal to mass times acceleration. Now notice that the net force, ma, which is what we're trying to calculate, is in fact equal to the force of friction itself. And at this point, all that we do is plug in numbers. Now the numbers themselves are the following. The mass, as it says in the problem, is 100 grams. Once again, we want to convert that into kilograms, however, by dividing by 1,000 grams per kilogram, that's 0.1 kilograms. And then I take that 0.1 kilograms for the mass here and multiply by just the magnitude of the acceleration that we found on the top board. We've already taken care of the directions from the force diagram itself and by adding up using F equals ma. So you just write it as a positive number, and this comes out to be 0.125 newtons. So a problem such as this is a nice means of jumping, if you will, from chapters 2 and 3, which is basically summarized here on the top board, kinematics, to now F equals ma and dynamics here, understanding the causes of motion. Okay, question?
Can you repeat what you said about negative and?
Yeah, you're going to see this. You're going to see me do this explicitly in the next example when I have forces acting on a single object in opposite directions. But the general rule that we'll always use, you'll see me do this over and over and over today, is any force vector that points in the same direction as A, we think of as a positive number, and any force vector in the opposite direction we think of as a negative number. Okay, to be explicit about that, let's look at the next example. Everybody's familiar with this situation. Let's see what happens if you take a ride in an elevator. And let's say that as you take a ride in an elevator, you stand on an ordinary bathroom scale when you do. And what we want to calculate is what the bathroom scale is going to read in the following situations. To illustrate, here's a bathroom scale. So, So a person with a mass of 75 kilograms is standing on a bathroom scale while in an elevator. What does the bathroom scale read for each of the following situations? A, the elevator moves at constant velocity. B, the elevator accelerates upwards at 2 meters per second squared. And then lastly, C, the elevator accelerates downwards at 2 meters per second squared. Now let's say I stand on this bathroom scale while I'm just standing here at rest in this classroom. So right now the two forces acting on me, the normal force upwards and the force of gravity downwards, just cancel each other out because I'm just sitting here at rest. However, when I stand on the bathroom scale, which of those two forces, the normal force acting on me upwards or my weight downwards, mg, which of those two forces does the scale directly read? I'll give you a hint. What the scale does directly read is the force of me pressing into it. That's the same thing, however, as which force acting upon me? The normal force by Newton's third law. Because remember, as I said, that yes, the scale reads the forces pressing directly into it, like so. But that's the same thing by Newton's third law as the scale pressing back upwards on me. That's the normal force. So in a context such as this, the normal force is sometimes referred to as the apparent weight. So that's what we want to calculate in each of the examples here. Let me just briefly summarize that for you here. So when standing on a bathroom scale, the scale directly reads, by means of a spring, by the way, the scale directly reads the force pressing into it. But by Newton's third law, which by the way we abbreviate as N3L, by Newton's third law, that's the same as the scale pressing back upwards. That's the normal force. So in this context, the normal force is sometimes referred to as the apparent weight. So that's what we're asked to calculate in this problem. The normal force itself, which is referred to as the apparent weight. So now, understanding that, what we want to calculate in each of these three situations is in fact the normal force. So now let's take a look at part A. So in part A of the problem, we have this elevator like so. Just draw it out of the box. Here you are standing in the elevator on a bathroom scale. And now in part A of the problem, it says explicitly that the elevator is moving at a constant velocity. So the acceleration is equal to 0. Does it matter if the elevator is at rest or is moving upwards at constant velocity or downwards at constant velocity? No, it doesn't matter. Because remember what one of the things that Newton's first law states. It states that there is no physical difference between an object at rest and an object that is moving at a constant speed in a straight line. So the actual motion of the elevator itself doesn't matter as long as the acceleration is equal to 0. Now, if the acceleration is equal to 0, the two forces acting on the person, the normal force upwards and the force of gravity downwards, they would just cancel each other out. And it's going to equal mg. So yeah, if you stand on a bathroom scale in the bathroom in the morning, for example, as long as your acceleration is equal to 0, the bathroom scale is reading your weight. But it's only doing so indirectly. What the bathroom scale directly reads is the normal force. As long as your acceleration is equal to 0, then yes, the normal force is equal to the actual weight of the person. But this is only explicitly for the case when the acceleration is 0. Now the numbers that we have here in the problem. We're given that the mass of the person is 75 kilograms. So let's go ahead and calculate what the normal force is, the person's weight in this situation in part A. And that's going to be 75 kilograms times 9.8 meters per second squared, which is actually 735 newtons. I'm kind of jumping ahead of myself in terms of the numbers. Don't be surprised, by the way, with big numbers associated with newtons. 1 newton is actually a lot smaller than 1 pound. You don't need to know this off the top of your head, but 4.45 newtons is equal to 1 pound. So just for reference, if you're interested, 735 newtons, if I divide by 4.45 newtons per pound, is about 165 pounds. So don't be surprised with big numbers associated with newtons. Okay, now the situation is going to change in part B. So in part B, here's our elevator once again with our person. And now in this case, the acceleration is upwards at 2 meters per second squared. Everybody here is intuitively familiar with this. I'm assuming that everybody here has been in elevators before. But imagine what happens when you first get into the elevator and the door is closed, and now it starts to accelerate upwards. What happens to you inside the elevator during the acceleration? Yeah, you kind of feel yourself get pressed into the floor. The reason for that is because it's basically the same thing as one of the scenarios that I described for you qualitatively last time in class, where you're in a car and the car is initially at rest. And then the car begins to accelerate forwards. Remember that relative to the ground that you remain at rest until something pushes you. That's the seat behind you. So from your point of view inside the car, it feels as if you got pushed backwards, but remember what's really happening is that the car that's accelerating ahead of you. This is essentially the same thing. You're remaining at rest while the elevator accelerates ahead of you until something pushes you. That's going to be the floor. So then therefore, if you were standing on a bathroom scale when this happens, is the scale going to read your weight or something greater than or less than your weight? It's going to be greater. Let's then see what happens. Now in this case, it's still the normal force upwards and it's still gravity downwards, but they don't cancel out in this case. The reason for that is because the acceleration is upwards. Now here's how we add up the forces in this case using F equals ma. Notice that the normal force is in the same direction as A. We think of that as positive, and now mg is in the opposite direction. We have to think of that as negative. So when I add these guys together, I then get n minus mg is equal to ma. So this is the sum of the forces still here on the left-hand side of the expression. N positive in the same direction as A, mg negative in the opposite direction. And then what we do is we just solve for n. So move the mg to the other side. Like so. And then now notice that what the scale here reads, the person's apparent weight is greater than their actual weight by this amount. This amount here, by the way, is 75 times 2, or 150 newtons. So 735 newtons from part A, plus an additional 150 is 885 newtons. So this 165-pound person, while they're in the elevator in this manner, feel as if they weigh, converting, about 199 pounds. And then lastly, part C. Once again, you're intuitively familiar with this. In this particular case, the elevator now accelerates downwards at 2 meters per second squared. So you've all experienced this before. You get into the elevator, the door is closed, but now the elevator accelerates downwards at 2 meters per second squared. What do you feel inside the elevator when this happens? Yeah, you kind of feel yourself be a little bit lighter. So then therefore, if you were standing on a bathroom scale, it should read something that is less than your actual weight. Let's see what happens. Okay, now in this particular case, it's still the force of gravity downwards, mg. It's still the normal force upwards, but once again, they don't cancel out. In fact, the force of gravity, mg, has to be bigger than the normal force in this case because the acceleration vector is downwards. Once again, here's how you approach the equation. In this case, it's mg that I have to think of as the positive number because that's in the same direction as A. The normal force has to be thought of as negative in this case because it's in the opposite direction. So when I add these guys together vectorially, it's mg minus n is equal to ma, like so. Notice that the equation there for part C is basically backwards of what it was earlier for part A, or for part B, excuse me. That's because we now have to think of down as the positive direction. And then I just solve for the normal force. So when I solve for the normal force, let's just reverse these two terms here algebraically. And you end up then with the normal force, the person's apparent weight being less than their actual weight by this amount. So numerically in this problem, it's 735 newtons minus 150 newtons, that then gives you 585 newtons, like so. So this 165-pound person, while they're accelerating downwards in the elevator, they feel as if they weigh, I'm doing the conversion here, about 131 pounds. And then lastly, for this example, just conceptually, let's consider the following scenarios. What would happen to you inside the elevator if it was accelerating downwards, not at 2 meters per second squared, but instead at 9.8 meters per second squared? What would happen to you inside the elevator? That's right, you would be in free fall. So if you were in free fall, what would the normal force, your apparent weight, be equal to? Zero. Be equal to 0. And in fact, it is. Take a look at the equation itself. So in that expression there, if the acceleration of the elevator downwards is equal to g, if the acceleration is equal to g, what happens to the normal force? And so mathematically, if the acceleration is equal to g, what is this equal to? It's equal to 0. This is what is specifically meant by weightlessness, when the normal force acting on an object is equal to 0. The objects would be in free fall. But then lastly, let's say that the elevator's acceleration downwards was not 9.8 meters per second squared, but it was instead bigger than 9.8 meters per second squared. What would happen to you then inside the elevator? Where would you be?
Top.
Yeah, you would be against the ceiling. So therefore, in which direction would the normal force be acting on? It would be downwards. Well, what happens in my equation numerically here? If the acceleration is bigger than g, what kind of number do you get?
Negative.
You get a negative number. Now, if you get a negative number, what does that mean about the direction of the normal force vector? It's not upwards, it's downwards. So yeah, you would be against the ceiling, and a normal force acting on you would be downwards. Now, if you're having trouble picturing that, it would just merely be the following. So right here's the elevator, here's you inside the elevator, and now what I'm going to do is put you inside the elevator, and I'm going to accelerate my hand downwards at a value greater than 9.8 meters per second squared. Watch what happens when I do. Like so. Notice that the eraser was against my hand the whole time. Let's take a short break.
So when the elevator's going down in 2 meters per second.
Wait. It's accelerating down to 2 meters per second squared. So if you want to think of it as moving downwards, now it's doing so, it's speeding up as it does.
Okay, so this accelerating at 2 meters per second squared on the scale. So when it stops, it's like the bottom force.
Okay, when it stops, then you would be decelerating, if you will. Your acceleration would be upwards. So it would be like part B, you would feel heavy.
So your weight would, when it stops, the elevator would decelerate, so your weight would be equal to as if it was.
So once you're at rest, then your acceleration is 0, and then the normal force is equal to your weight function.
Okay, but I mean, I'm talking about at the moment that you're decelerating with your weight, because as you're going down, as you're accelerating downwards, your weight is lighter than your.
Wait, you have to phrase things properly here.
I'm sorry.
Okay, your apparent weight is less than your actual weight
Right.
while you're accelerating downwards.
Correct.
Your apparent weight is greater than your actual weight while you're accelerating upwards.
Right. So my question is that if you're accelerating downwards, will your apparent weight be greater or less than your,
So while you're accelerating down, you're speeding up while moving downwards,
Right.
then your apparent weight will be less than your actual
will be
weight.
less, but then then
Okay, so when you get down to the bottom and you slow down, when you slow down, remember your acceleration vector is up.
Yeah.
So then the normal force will be the bigger force than gravity, your apparent weight will be greater than your actual
Okay.
weight. Okay?
went skydiving as if you went in like a plane that was a
Mhm, yeah, absolutely. Now, when you skydive, however, there is a large amount of air resistance acting upon you, so you wouldn't be in free fall for very long if you first jump out of the plane, because air resistance is a non-constant force that actually builds the faster and faster the more you move through the atmosphere. It's essentially because there's a greater and greater pressure buildup. So you eventually get to a point where you reach what is called terminal velocity. That's when, as you fall downwards, your acceleration is actually equal to 0. You move downwards at constant speed. They're all in their jammies too.
Are all your classes like this?
No. For whatever reason, you guys seem to be a little bit tired.
It's like almost 2 o'clock. That's pretty.
I know, it's pretty intense. It's almost 2 o'clock.
I
Did you
know.
know it's actually 2 o'clock twice per day?
You got me there.
Sorry. All right, Nathan, inside time. All right, next, let me go ahead and move on. All right, guys, wake up, stay with me. You can do it. Stay with me. All right, now notice in my examples thus far, when I draw my force diagrams, I treat the individual objects as points. And then I just apply the force vectors to those points, and then we add things up and go from there. What allows me to get away with it? Why don't I have to, for example, take into account all the individual atoms and all the forces that occur between the atoms that make up these objects? There's actually a very specific physical reason for that. I'll answer that question in the context of this example. In this example, let's say that we have 2 books that are placed in contact with one another side by side. We put them on a horizontal frictionless surface. And by the way, there's no such thing as a frictionless surface. We'll examine forces of friction a little bit later on in chapter 5, but for now we'll simplify the situation. We put them all on a horizontal frictionless surface, and then I come along and just exert a horizontal force, in this case of 10 newtons to one of the books, like so. And we want to calculate the acceleration of these books. As I work through the example, we'll see physically why I actually don't have to take into account all the forces that occur between all the individual atoms and blah, blah, blah that make up these objects. So 2 books are placed side by side in contact with one another on a horizontal frictionless surface. We'll say the masses of the books are 1 and 2 kilograms respectively. I then apply a horizontal force of 10 newtons to one of the books, find the acceleration. The acceleration of the books will be the same because they're in contact with one another the whole time. Okay, now picturing my situation here is easy. We have this horizontal frictionless surface. And then I have my 2 books. So on your left, the blue book, we'll say that's M1, we'll call it. It's 1 kilogram. And then on your right, the white book, let's call that M2. That's 2 kilograms. Okay, and then I apply a force here horizontally to the left-hand side. Let's just call it F push. That's equal to 10 newtons. And then the books accelerate at some value A to the right that we want to find. Okay, we examine the problem by looking at the forces acting on each individual object. This is our first example, by the way, of 2 objects in a system. We examine F equals ma by looking at the forces that are acting on each individual object. We do so separately. So let's take a look at, first of all, the blue book, M1. So then, therefore, ignoring friction on the table, vertically and horizontally, how many forces are acting on the blue book when I do this?
After you release it?
So vertically and horizontally total, how many total forces act on the blue book, ignoring friction, when I pushed it to the right-hand side?
Including?
That
Okay,
includes.
so vertically and horizontally, how many total forces? We'll see 4. Here's how they work. Okay, first of all, there's some obvious stuff. We have, first of all, the weight of the blue book, M1G, and then then the normal force upwards, N1 we'll call it. These forces cancel each other out vertically. Vertically, there's no acceleration. Okay, then yes, I push on the blue book to the right-hand side with the force F push. But as I said a moment ago, there is a fourth force that is acting on the blue book. How would you describe it, and in which direction does it act? Elena?
I would say if the white book would be back against the blue book, right?
Okay, she's correct. Here's how we phrase
Oh,
it.
sorry.
You have to be very careful with your phrasing. This is the force on one due to, like so. And now horizontally, keep in mind that the acceleration is to the right-hand side. I now add up the forces in the following manner. F push to the right-hand side in the same direction as A will be positive, and this force here in the opposite direction will be negative. So when I add up the forces here horizontally, I get F push minus the force on 1 due to 2 equals the net force. And we're specifically talking about object number 1, so the net force is just M1A. Notice in the equation that there are two unknowns. One of the unknowns we want to find, that's the acceleration A, and then the other unknown is the force on 1 due to 2. This equation here is no help algebraically, so then therefore I have to come up with another equation. Another equation is obviously found by taking a look at the white book, M2. So with the white book M2, when you, once again, see me do this, and ignoring friction with the table, how many total forces, horizontally and vertically, are acting on the white book?
4.
So ignoring friction with the table,
Oh, 3.
that's right, there's 3. Okay, now 2 of them are rather obvious. We first of all have the normal force upwards, N2 we'll call it. Gravity downwards, N2G. These guys just cancel out. But then how would you describe the force acting to the right-hand side on the white book that gives us the acceleration? Is it just F push that's acting on the white book?
No.
No, it's not, because I'm pushing on the blue book. So what actually pushes the white book, Lena?
Force on 2 to the 1, right?
She's exactly right. So we have force on number 2 due to number 1. And now we just add things up here horizontally. In this case, it's easy. There's only this one force. So we have the force on 2 due to 1 is equal to the net force on number 2, which is M2A. So with these two equations that I have here horizontally, this one here acting on M2, and that one there above acting on M1, initially it looks like I have 3 unknowns. One of the unknowns is the acceleration that we want to find, but then secondly and thirdly, I have the force on 2 due to 1, and also the force on 1 due to 2. But what do we know about these two forces? They're equal to each other by Newton's third law. They're equal and opposite reaction pairs. So this guy right here, and this guy right here are equal by Newton's third law. They're equal and opposite reaction pairs. And the directions being opposite has already been taken care of, notice, in the equation. This one here points to the left-hand side. This one here being positive points to the right-hand side. But yes, those are equal and opposite reaction pairs. Because they're equal and opposite reaction pairs, what this then means is that algebraically, I just have 2 equations and 2 unknowns. So now what I do is I take this force on 2 due to 1, which is M2A, and I just plug it into the equation above. So what I do with the equation above, I get F push minus M2A is equal to M1A on the right-hand side. And now I just begin to solve for A. When I solve for A, I move this term here to the right-hand side. When I do, by the way, I'm going to factor out the acceleration from each term because it's common to both. And I arrive then, therefore, at this step right here. Now notice what this equation is saying before I finish by just dividing by the parentheses on both sides. It's as if I'm just pushing on one object, total mass M1 plus M2. It is specifically for this reason that I don't have to examine all the forces that occur between all the atoms and blah, blah, blah that make up these objects. It's because through Newton's third law here in the equations themselves, everything adds together to give you to this step right here, where it's as if you're pushing on a single object of total mass, in this case, of M1 plus M2. So that's why it's perfectly fine for me to draw my force diagrams as if the object itself is a point and then go from there. And then I just finish the example here numerically by dividing by the parentheses on both sides to get the acceleration all by itself. Like so. And then therefore numerically it's 10 newtons here in the numerator divided by a total of 3 kilograms in the denominator. 10/3 is 3.33 meters per second squared for the metric SI units of acceleration. Once again, what you're seeing here in this example is explicitly how Newton's second and third law kind of act together to arrive at this expression here. Okay, question?
You know when you say F on 2, 0, 1?
Yeah, you gotta be careful with your phrasing, because the reason why I phrased it like that is because, yeah, these guys here are equal and opposite reaction pairs by Newton's third law.
Okay, but I mean, like, so you're pushing on the blue book.
Okay, so I push on the blue book,
Okay.
and then therefore the blue book pushes on the white book, but the white book pushes back.
Okay.
Okay, so how the blue book pushes on the white book, and then how the white book pushes back on the blue book, that's these guys here, which are equal and opposite reaction pairs.
But if you push on the blue book, wouldn't it push back on your hand?
Yeah, it does, but I'm not talking about the forces on my hand. We could if we wanted to,
okay.
but we're not explicitly looking at that in the problem. We're only looking at the forces on the books themselves. Now, last time in class, when I was demoing all these various situations involving Newton's laws qualitatively, one of the demonstrations that I did involved an air track on my desk. That air track problem, as I call it, is going to become your next major laboratory exercise. We'll actually do that laboratory exercise on Friday of this week, and it will become the next major laboratory report. However, it's useful for us to take a look at it as a problem first, and then at the end of the problem, we'll understand exactly how it will link with our lab at the end of the week. Okay, but let's take a look at it, first of all, as a problem. And yeah, I call it the basic air track problem. Now, as we go through the context of this example, we'll see once again lots of simplifications that occur in this example. Now, we kind of looked at this problem qualitatively last time in class with the demonstrations as I described them. Now we'll go through it numerically. And then we'll see at the end of the problem how it essentially will become our next major laboratory exercise. Okay, once again, there's some idealizations that are being described here in the problem. We'll see how they're important. Okay, now if you recall from last time, the air track situation kind of looks like this. The air track itself, first of all, is horizontal and frictionless, and that's how we'll set it up as best we can on Friday of this week. And then we have two objects. We have the cart itself, M1, and then the string draped over this pulley like so, and the second object here off to the side, M2. Okay, just numerically in this example to make the numbers easy to work with, M1 and M2 are the same thing, just 1 kilogram. And then we saw the acceleration when I turned on the air, look like this. Okay, now here's once again some idealizations. Like before, we considered a string to be massless, and the tension at all points on the string itself, whether it be here or here, etc., is always the same number. When the string is taut, it's a perfectly straight line, doesn't sag under its own weight. that immediately means that this line right here is parallel to the horizontal surface, and this line right here is vertical. Okay, now remember what happens, however, in reality. In reality, as the object, say, accelerates in this direction, more and more string over here gathers, if you will, overhanging this side of the pulley. So in reality, what happens to the amount of weight of string that you have over the side of the pulley as the acceleration occurs? It increases. What this means is that the acceleration is actually not a constant as the weight of the string here increases over the side. When it occurs, that is, if you have a non-constant acceleration, F equals ma is not an algebraic equation like we're seeing it in these introductory examples. Instead, it's a differential equation. And the only way to solve it mathematically is by using the techniques of calculus. We're ignoring that complication here. So this is one of the reasons why it's important to consider the string to be massless, because in reality it's not. That actually means that the acceleration is not a constant. We're ignoring that complication. Okay, and then we get to the pulley itself. It says that the pulley is frictionless. What the heck is that? Okay, well, here's a larger pulley for a separate problem that we'll treat a little bit later on, but let me demo this situation here in this context. Okay, now in reality, there is, of course, friction between the string and the pulley itself. So watch what happens when I let go of this and the objects accelerate. Notice that the pulley rotates, like so. In a realistic situation, the pulley's rotation has to be taken into account. That's a complication that we want to ignore for now. So then therefore, if the pulley is frictionless, what that then means is that the pulley doesn't rotate, and the string just slides on it like so on a frictionless surface. All that this then simply means is that what the pulley really just does in this situation here is it redirects the tension around the 180-degree angle. In this problem here, it just redirects it around a 90-degree angle, but that's essentially what the function of the pulley is when the pulley doesn't rotate. The string just slides like so on a frictionless surface. So the pulley is frictionless, but then makes the problem easy to deal with mathematically. I'll fix it later. All right, now we begin when the air is on and this situation occurs by looking at our forces here on M1. I actually drew out for us already this force diagram from last time in class. Remember that it basically looks like this. Now with, however, all the symbols. We have, first of all, the normal force upwards, M1 we'll call it, and the weight M1G downwards. This is a horizontal situation, so M1 and M1G just cancel each other out. And then it's the tension from the string here that pulls to the right-hand side, thereby giving us our acceleration vector. And then now horizontally, I just add everything up. We have nothing more than T is equal to M1A. Okay, like in the last problem with this opening equation here, I basically have two unknowns. One of the unknowns, by the way, always, when you have two objects connected together in some manner, one of the unknowns is always the force that occurs between the objects themselves. We're usually not so concerned with that. Instead, what we usually want is the other unknown, which is the acceleration A. So in order to get that, I need another equation. That's obviously going to be found by looking at the forces here acting on M2. So with M2, two forces acting on it, tension upwards, gravity downwards, M2G like so, and the acceleration is downwards. Now that you've seen me do this a few times, by the way, who thinks that they can give me the equation F equals ma for that force diagram in this situation here for the M2? What is my equation F equals ma from that force diagram? Who thinks that they can get it? Remember the basic rule. Any force vector in the direction of A is positive, any force vector in the opposite direction is negative. So how do you add these guys up then using F equals ma from that diagram? Who thinks they can do it? Yes, no?
Is it M2G minus T is equal to M2A?
She's exactly right. Like so, she got that by noting the following. M2G here is in the same direction as A. Think of that as a positive number. tension in the opposite direction is then therefore negative. So what you end up with here are basically just two equations and two inputs. That's usually how these problems go, involving two objects that are connected together in some manner. We'll see that with this pulley problem in a few minutes as well. Okay, and then algebraically, we just have to combine stuff together. We'll take the expression that we have here for tension, which is M1A, and just plug it into here like so. And then we just run through the remainder of the algebra here to solve for A. So you move this term to the other side, and you can factor out the acceleration from each term as you do. Once you become proficient in doing this with a little bit of experience, you can kind of begin to combine some steps together here algebraically, at least the easy stuff. Like so. And then the last step here is just to divide by the parentheses on both sides. And so then therefore the acceleration of this system, as we saw it last time in class with the demonstrations, is the following expression. Now numerically I set this problem up to be easy. We just have 1 times 9.8 divided by a total of 2 kilograms. This works out to be 4.9 meters per second squared. And now here's how this problem is basically going to become our lab exercise on Friday of this week. What we'll do is set up the situation here in blue on the top board, and then you're going to attach a piece of strip tape to M1. And then using a spark timer, like we did, for example, back in the Chapter 2 free fall lab, what you'll do is you'll turn everything on, let the acceleration occur, and then use the spark timer to measure the acceleration. We'll measure it exactly the same way as we did the free fall lab back in Chapter 2. And then once you have the acceleration measured, then we'll compare it to what it theoretically should be. According to Newton's second law, the acceleration should be this quantity here. So we'll calculate this quantity and compare it to the acceleration they actually measure using the spark timer with a percent error. If all goes well, of course, the numbers should be the same. That's basically what we'll do as our lab exercise on Friday this week. Okay, okay, next. Okay, next is specifically this example here involving just a single pulley. You have a very common basic problem here involving a single pulley that is introduced to most introductory physics students. This right here is referred to, by the way, as an Atwood's machine. We use the word machine in this context for the following reason. All that a machine really does fundamentally is redirect forces. Regardless of how simple the machine may be, using a single pulley like so, or how complicated a machine may be, such as an internal combustion engine. All that a machine really does at a fundamental level is redirect forces. In this particular case, this single pulley here redirects the tension vector around a 180-degree angle. What we want to do with these masses here is set this situation up and find the acceleration of the objects like so when I let them go from rest. It's very similar to this example here, but it is a basic example that all introductory physics students see. This is referred to, as I said, as the Atwood's machine. It's named after somebody. Now I set up my demonstration here with approximately those masses there in mind. Okay, on your right-hand side, kind of with the little washer attached to it like so, is the 15-gram mass, and then on your left-hand side is the 10-gram mass. And we'll once again consider the pulley here to be frictionless, so the string just slips on the pulley. It also says that the pulley is fixed. What that means is the pulley can't move up or down or sideways or anything like that. And then the easiest way to visualize the problem is just to release the objects from rest like so, and then calculate what the acceleration is. As we do this, however, we're ignoring the rotation of the pulley itself. Okay, now the Atwood's machine problem is very simple. We have here a pulley like so, and it's fixed in place, as usually indicated with a little dot right here in the center. And then we've got our string draped over the pulley like so, with our two objects. Now I have this set up such that the lesser mass is on your left That's 10 grams, but we do have to convert it into kilograms. Be careful when you do so, by the way, remember that there's 1,000 grams in a kilogram. So if you take 10 and divide it by 1,000, that mass M1 is 0.010 kilograms. This is, by the way, an easy mistake to make in converting grams into kilograms. Be careful of that. Okay, then this here on your right is the M2 of 15 grams. Divide that by 1,000. That's 0.015 kilograms, like so. And then as you saw, when I released the objects from rest, they accelerated like this. The acceleration is the same number because the string is once again taut. Okay, now we just set up our force diagrams, and then from there get F equals ma for each object, and then do the algebra. It's very similar to the last example that I did. Okay, first of all, for the object here on the left, M1, we have the following forces. Tension upwards, M1g downwards, and remember that the acceleration of M1, the lesser mass, is upwards. Okay, once again, you've seen me do this now a bunch of times here today. Who thinks they can give me the equation? What is F equals ma for that force diagram? Go ahead, Nash.
M1g equals T minus
Mhm.
M1a. Okay.
No, do sum of the forces equals M1a. So you're going to have something equals M1a on the right-hand side. So how would you sum the forces, though?
M1a equals T minus M1g.
Yeah. So you have T minus M1g equals M1a. So we got that by noting that the acceleration is upwards, that's the positive direction. So T is the positive force, and then the weight M1g in the opposite direction has to be negative. Okay, like in the last couple of examples, notice that there are two unknowns. One of the unknowns is the force that connects the objects. We don't really care about that. And the other unknown is the acceleration. So then we take a look here at M2. So when we look at M2, make that a little more distinct. We have tension upwards still and the weight M2g downwards. But now with this object, remember that the acceleration is downwards, like so. So what's my equation here? What's my equation here?
M2g minus T equals
Okay,
M1a.
those of you that are chattering it out,
M2a.
should get this right here. Okay, in this case, the acceleration being downwards is the positive direction. So M2g is the positive force, tension in the opposite direction, and therefore is negative. And then boom, boom, there it is once again, two equations, two unknowns. So a lot of these problems are very similar in that sense. Got to be a little bit careful when you do the algebra here. What I'm going to do is take the top expression and solve for t. So we'll move the M1g to the other side like so. And then take that expression for the tension and plug it into here. But when you do, be careful to distribute this negative sign through both terms. That's an easy mistake to make. So I'm going to have first here M2g and then minus t. So minus both of those terms there. Like so, equals that M2a. It's a very easy mistake to make to forget to distribute that negative sign. Okay, and then the remainder of the problem is merely the following. Take the M1a and move it to the right-hand side. I'll do a little bit of factoring when I do as well with the common acceleration. Once again, a couple of minor steps here done together, like so. And then just divide by the parentheses on both sides to get the acceleration. And you end up here with an acceleration that looks very similar to the acceleration that I had in the previous problem involving the air track. A lot of these pulley problems that you'll see at the introductory level all kind of work the same way. When you do eventually solve for the acceleration, what you'll end up with is some combination of weight in the numerator divided by total mass in the denominator. That's usually how it works out. Okay, now I'm going to use my calculator for this one because of the strange numbers. I have first of all in the numerator M2g, so 0.015 times 9.8, minus M1g, 0.010 times 9.8, and then divided by a total of 25 grams there in the denominator, 0.025 kilograms. This works out to be 1.96 meters per second squared. Now that acceleration that I just calculated here in this example, it has nothing to do with the initial motion of the objects. That doesn't matter. So for example, it's just easy to picture. If I start with the objects at rest and then let go of them, and then boom, that happens. They accelerate exactly as we calculated. However, what would happen if the objects were initially moving like this? Well, if they were initially moving like that and then I let go of them, that happens. They still accelerate exactly as I calculated in the directions that I've indicated. So if I just initially move it like so, and then I'll let go of it, they just continue to speed up in their direction of motion. But what would happen if, for example, this object right here, which accelerates downwards, remember, at 1.96 meters per second squared, what would initially happen if the object was initially moving upwards like so, and then I let go of it? What would happen to it? Well, it would just slow down and stop, and turn around and move in the opposite direction. The whole time that that object was doing that, however, it was accelerating downwards at 1.96 meters per second squared. It's like, for example, taking an object and throwing it upwards in free fall. It moves upwards and slows down as it does, and then speeds up in the opposite direction. The whole time that the keys are in free fall, however, they're accelerating downwards at 9.8 meters per second squared. In this particular case, this object, if I do this, the whole time is accelerating downwards at 1.96 meters per second squared. But it's similar to taking an object and just throwing it vertically upwards. Now, in the examples that I've done here thus far today, they're kind of intuitively obvious as to what's going to happen. It's intuitively obvious in this Atwood's machine example that the objects are going to accelerate in the manner that we indicated. But sometimes in problems, and maybe a little bit more complicated, it may not be so obvious what the direction of the acceleration is going to be. So what happens if the direction of the acceleration is not so obvious? All that you do is just choose a direction for the acceleration and then go from there. And then what it is that you calculate will tell you what has to happen. For example, let's say that I look at this problem, let's say I don't have much common sense. Let's say I look at this problem and I say to myself, you know what I think it's going to do? I think it's going to do this. So, what would happen if I made that assumption? Well, if I made that assumption, I would look at M1, for example, and I would obtain the following. We have the weight downwards, the tension upwards, and the acceleration is downwards by assumption. So when I add up the forces here, if I think of it in this manner, I'll get M1G minus T equals M1A. Note that that equation there is basically backwards of how I wrote it a few minutes ago. And then I would look at M2. Okay, M2, that's tension upwards, M2G downwards. I'm assuming the acceleration is upwards. I would add up the forces there, and I get T minus M2G equals M2A. This equation here is once again backwards of how I wrote it a few minutes ago. And then you would do the algebra, blah, blah, blah. You would eventually solve for the acceleration, and here's what you would obtain. You end up with this expression here after you did the algebra. Now, how does this expression here compare to how I wrote it a few minutes ago? What do you notice about the numerator?
Negative.
The terms are reversed. So if you plugged in the numbers here, here's what you would end up with. Negative 1.96 meters per second squared. Now, the negative sign does not mean that the objects are slowing down. That's not what it means. What does it mean about the direction of the acceleration vector in terms of what I assume? It's in the opposite direction. So in other words, the negative sign that I get here means that the acceleration vector here, which I thought was upwards, is in fact downwards. And then therefore this one here is in fact upwards. So the acceleration is in the opposite direction. So did I do the problem incorrectly? No, as long as I know what the acceleration being negative here means. And that's perfectly fine as the answer. So basically all that you do is just assume a direction for acceleration and then calculate it. If you end up with a positive number, then you guessed right. If you end up with a negative number, it's just in the opposite direction of what you guessed. However, you did something like this, and then what would happen? You come along and you have no common sense whatsoever. And you look at this and you say, oh, I know what I think it's going to do. I think it's going to do this. While the string is taut. Or you come along and you say, you know what I think it's going to do? I think it's going to do this while the string is taut. If you set up your equations that way and then calculate the acceleration, you'll end up with mathematical gibberish. You'll end up with blah, blah, blah equals 0. You'll end up with like 5 equals 0. So if you end up with mathematical gibberish, what does that physically mean about the situation? It means it literally can't happen. It means it's physically impossible. It's physically impossible for the string to be taut and the objects to accelerate like that. It's physically impossible for the strings to be taut and the object to accelerate downwards in some manner like that. It means it literally can't happen. So if you set up a situation and you end up with nonsense mathematically, it literally is nonsense physically. It means that it physically can't happen. Okay? Okay, any questions thus far? Go ahead, take a nice deep breath. I'm going to be finishing today, excuse me, with one more example. But this example, which is, by the way, very important, is a little bit different than what you've seen me do thus far. In all of the examples that I've done thus far, I've kept it as easy as I possibly could. What I mean by that is all the force vectors in these situations acting upon these objects have always either have been perpendicular to the acceleration or parallel to the acceleration. What happens if you have a force vector that is instead on an angle with respect to the acceleration? We'll see that with our last example here for the day. This is a very important example, and you'll see for a lot of reasons. That's the frictionless incline. Now, just to keep it simple to picture, let's just say that we start with our object here at rest on the incline. The incline is frictionless, and I let go of the object, and it accelerates down the slope. We want to calculate what the acceleration is. There are only two forces acting on the eraser in this situation if we ignore friction. And that's gravity straight downwards and the normal force. As we'll see, the normal force is still going to be perpendicular to the surface. But notice immediately a complication just when you look at it. The acceleration is down the slope in this direction like so. The force of gravity is straight downwards. In other words, the force of gravity is on an angle with respect to the acceleration vector. How do we deal with that mathematically in this situation? Well, let's begin to see. Okay, first of all, the basic incline is just drawn like so. Right here is our angle of inclination. This is given to us theta, is 30 degrees. And then here's our object of mass m. Notice that the mass of the object, however, is not given in the problem. And then, as I said, as the object slides down this frictionless incline, there's only two forces acting on it, thereby giving us the acceleration down the incline, as we saw. The two forces are the normal force, still perpendicular to the incline, and mg straight downwards, like this. Okay, now as I said a moment ago, the normal force is in fact perpendicular to the incline. It's not immediately obvious, however, why that has to be. But imagine for a moment that the normal force was not perpendicular to the incline. Imagine that the normal force, instead of being perpendicular to the incline, somehow instead pointed down the incline. In other words, it kind of looks like this. Stay off the side. Don't draw this. Right, here's gravity straight downwards like so. And let's say the normal force is kind of tilted at a strange angle, like that. Well, what this would then mean is that the normal force would have components. It would have a component that is perpendicular to the incline, and a component that is parallel to the incline. And notice this parallel component here points in the same direction as the acceleration vector. What this would literally mean is that somehow the incline itself is pushing the object down the incline. That would look a little weird. What would that look like? Well, if the incline itself could somehow push the eraser down the incline, it would literally look like this. That's a little strange. Hey, what would happen, however, if instead of the normal force being perpendicular to the incline, imagine if it pointed, say, slightly up the incline? What would happen then? That would look a little strange too. So now imagine taking that normal force vector and doing something like this with it, like that. Once again, it would have components. It would have a component perpendicular to the incline like so, and a component parallel to the incline. And notice this parallel component is opposite of the acceleration. What this would literally mean is that the incline itself is trying to somehow push the eraser up the slope. That would look a little strange. That would look like this. So, okay, now yes, obviously, I'm being a little bit facetious here. The technical reason for why the normal force has to be perpendicular to the slope, for example, is because if it was, the energy necessary to push the eraser down the slope or up the slope would have come out of nowhere. It would literally violate conservation of energy. We'll see exactly why that is when we get to energy, specifically in chapters 7 and 8. But if the normal force was not perpendicular to the incline would have the ability to push the eraser down the slope, or push the eraser up the slope. The energy necessary to do that would have come out of nowhere. It would imply that energy was created. So that is the technical reason for why the normal force has to be perpendicular to the incline. Zach, you had
Chapter 7 and 8 this semester.
So chapters 7 and 8, yes, are into the end of this semester and into the beginning of the next. Basically here in chapters 4 through 6, you get introduced to forces, and then in chapter 6, exactly how gravity works as a force. And then in chapters 7 and 8, you start to learn the nuts and bolts of energy transfer and conservation of energy. Okay? That's the end of this semester and a little bit into the second semester as well. All right, so suffice it to say then, our normal force has to be perpendicular to the incline, as I've indicated here on this diagram. However, we still kind of have a problem. The acceleration vector is like so, whereas gravity, however, is on an angle with respect to the acceleration vector. Here's how we deal with force vectors that are on an angle with respect to the acceleration. I actually was sort of already doing this on the right-hand board. What we have to do is we have to take, in this case, gravity, mg, and break it into components. We have to break it into a component that is perpendicular to the acceleration, and then a component that is parallel to the acceleration. We break up mg into these green components because, as you'll see in a moment, when we do the geometry, this angle right here is the same as the angle of inclination. This right here is the angle theta as well. Now, why is that so? Where does that come from? Well, just a little bit of basic geometry. On the incline itself right here, here's the normal force, and here's the weight of the object, mg. Now, just to show the geometry of how this angle here is in fact equal to this one here, we begin by right here at this location, drawing a line that is parallel to the base of the incline. If this dotted line right here is parallel to the base of the incline, then the angle theta here in blue is obviously the same thing as this. Okay, now I've got my green components here. Like so, and like so, where right here is the angle that I'm trying to show that is in fact equal to theta. Okay, take a look at this red angle here. Note that this right here is a right angle. So if this right here is a right angle, in terms of the green theta, what is this red angle here? It's 90 minus theta. So, okay, now next, right here is a right angle. So if the red angle is 90 minus theta, then what does this green angle have to be? It has to be theta. So that's the geometrical proof that shows that yes, in fact, this angle theta, this guy right here on this diagram, is equal to the angle of inclination. So that's one of the reasons why we break up mg into those components, so we see the angle theta directly. Now, how do I add things up here? Well, in this perpendicular direction, there's no acceleration, so everything cancels out. The normal force here doesn't cancel out with mg. and instead it cancels out with this adjacent component here of mg. Think of this as a little vector triangle where the hypotenuse of the triangle is the weight mg. This right here is the adjacent side of the triangle. What is the adjacent side of the triangle equal to?
Really,
It's
doing.
hypotenuse times cosine of theta. So this guy right here is the hypotenuse mg times cosine of theta, like so. So the normal force here, like so, perpendicular to the incline, cancels out with this component of mg cosine theta. But now take a look at this guy right here, the opposite side of the triangle. Notice that it's the opposite side of the triangle here that gives us mass times acceleration. Now, what is the opposite side of the triangle?
G sine theta.
That's right, it's hypotenuse mg times the sine of the angle theta. So this mg sine theta here is the only force that points in the direction of A, so then therefore mg sine theta is equal to the net force, ma, like so. So that's how you add up a force vector when it's on an angle with respect to the acceleration. You break it up into a perpendicular and parallel component like so. Now take a look at the result of this equation, where what we have here once again is the mg sine theta giving us mass times acceleration. Notice that the mass of the object cancels from the expression, and the acceleration is a constant. It's a constant regardless of the mass of the object. Where have we seen this before? Where on a frictionless incline, the acceleration of the object does not depend upon its mass. Where have we seen that? It's Galileo's free-fall experiment. Remember what Galileo did? He took a frictionless incline, tried to make it as frictionless as he could, and then he set objects of various weights, various masses on the incline, and he measured their accelerations. And he found experimentally that the accelerations were all the same number regardless of the mass of the object. So what I've done here using Newton's laws of motion is I actually have derived Galileo's free-fall experiment. This is Galileo's free-fall experiment explained. Now, before I plug in the number here for our particular problem, just look at the equation here one more time before I do so. Imagine that the angle theta here is not 30 degrees as is described in the problem, but instead the angle is instead 90 degrees, like so. Take a look at the expression. What is the sine of 90 degrees? It's 1, and the acceleration then therefore would be equal to g. All objects accelerate downwards with the same constant acceleration of 9.8 meters per second squared. So yeah, it's Galileo's free-fall experiment, now explained using the laws of motion. Then just to finish the example here, we're given in our problem that the angle theta is 30 degrees. We did so for the following reason. What is the sine of 30, if you remember? What is the sine of 30? It's 1/2, so it's easy to work with. The acceleration is 1/2 of g, and it's 4.9 per second squared. So this example is important for a lot of reasons. Number one, yes, it's important historically. It's Galileo's free-fall experiment. But in addition to that, in terms of just nuts and bolts calculation, we have now another rule, if you will. Whenever you have a force vector on an angle with respect to the acceleration, you break up that force vector into components. We'll see this with more examples next time in class on Wednesday. Love you, Chandler. I'm finished.